So thanks for everybody coming in here. Just to introduce you all, I've been, again, I know Rahul just gave me introduction, but my main area of my focus has been process engineering. So processing on the production floor is where I get involved in. I worked for a couple companies before I started my company, my consulting company in 2004. So I've been in the business for the last 10 years. This is a very interesting topic for me, and that's the reason I also agreed to talk about this, is because as a processor, I find a lot of issues with parts, and it's too late at that point to make any changes either in the part design or in the mold design. And get good parts, good acceptable parts. If it's too late, it's too expensive, or then you don't get quality parts there. As a part of my business, like I said, I do a lot of consulting, and that's why I come with a lot of issues that I was telling you about. I was just at one of the facilities here in northern United States, where they built a huge mold. It runs about a 2,000-ton mold machine, and they have realized that there's been maybe an issue with the way the part is designed. There's a thick section one side, a thin section one side, and they want the part to be perfectly flat. It's too late. It's too late to change any of these things. So I got into this mainly as a consultant for processing, but I also do a lot of seminars here in San Diego, and I teach these things that I'm going to talk about. It's a very small portion that I do. I teach mainly processing. I'm also a contract faculty at UMass Lowell and UC San Diego. Whenever they have a requirement, I teach at UC San Diego, but UMass Lowell, I just came back from UMass Lowell last week. They had their session there. I do have a software for design of experiments, which I'll show you a little bit of screenshots from there. I won't show you the software, but anybody is welcome to take 30-day trials with that at some point. Also do research, R&D, self-funded on various things related to injection molding. The book was published in 2010, did really well. I'm actually working on the second edition now. It should be out early next year with a lot of new information. Of course, there's basic information also, but there's lots of new stuff that I have put in there. Having said that, let's understand what process capability is, right? So what do we mean by that? We have to first understand variation. So there's variation everywhere, right? The time it takes to come to work, the amount of gasoline that you use every week, although you go to work and come back, right? This is the amount of gasoline you could use is different. The amount of electricity bill, part weights in injection molding, right? You go weigh 100 parts that come out of the molding machine. They're all going to weigh different, right? If you don't see a difference in the weights, that means the weight scale is not accurate enough to measure to the decimal where the variation is. So there's always going to be variation in the parts, right? So to make a molded part, you can get variation from the machine, you can get variation from the environment, from the personnel, materials, the process, and measurement systems, right? Multiple things you can get variation from. So what they do is, right, we have to understand where the variation comes from. We cannot eliminate the variation, and part design is one huge thing which causes variation in the molding process, and that's what I'm going to talk about today, right? So we have to understand where this variation causes, so that we can reduce it. You cannot eliminate variation. If you have got a normal variation, the common cause variation that you see on the top over here, that's what's called a normal variation. You'll always get what's called a bell curve. That's called a normal distribution. That means you'll get an average part weight of 4.15 grams, but there will be some parts that are lower than that, some parts that are higher than that, right? So you always have this variation, and this variation can be of any shape, any size, but they all typically maintain the same bell curve, as it's called, right? So the reason you need to understand variation in a process is because if this is your nominal, the green one here, this is your lower spec limit and upper spec limit, and if this is your natural variation in your process, right, then what happens is that the molder will measure this part and say the parts are good, but unfortunately the customer measures these parts and say the parts are bad, right? It's the same exact process. Nothing has changed except what? you have taken this, molder has taken this side of the parts, and the customer has taken out these set of the parts, right? So for that reason, then of course, customer says you made bad parts, and the molder says no, we shipped you good parts, and it's actually the same one and same part. So you have to understand what the variation is in your process, right? Being in spec does not mean the process is capable. Remember that, right? So I'll talk about what capability is, right? So when you talk about capability, is basically this is your nominal, right? This line here is a nominal, and this is your lower spec and upper spec limit. You can get all sorts of distributions like this, right? You can get distributions anywhere inside this, and all these parts are going to be acceptable. So what they do is they do something called CPK calculation. So what CPKs tell you is that if the CPK is basically high, I won't go into details here, if the CPK is a high number over say 1.33, then the chances of the parts being within specifications is good. That means it looks something where all these parts are between the lower spec limit and upper spec limit. Anything above that, you're almost certain that the parts are all going to be good and within specifications. So they say CPK is basically a measure of how good or where the distribution is in relationship to the lower spec limit and upper spec limit. So just for now, just the take home from this is that if you're above 1.33, you're good. There are some parts on the lower spec on this side and this side, say 0.3% of the part that are bad, which of course is not acceptable in automotive. But if you're let's say at 1.66, then your part is definitely good. If the CPK is 2, that means all the parts are going to be within specifications, right? So basically, remember this as that higher the CPK, the better your confidence is, right? So then that's what that is. So if you look at the aim of the molding operation, basically you want to make sure you mold all the parts consistently, they meet all the quality requirements, and and that they're always in specifications, right? But see, to have good parts, good quality parts, there are 5 things that are extremely important, okay, to make good parts. The absolute first one is the part design. If you do not have a good part design, you're not going to get good parts. The second thing is the material of the plastic material being molded. That's the second thing that's important. The third thing is the mold design and the build. Okay, that is an extremely critical thing. The fourth one is the selection of the molding machine. So for whatever reason, always they say it's like the 4 wheels of the car, but if for whatever reason they forget the molding machine. And some people say it's part of the process, but I keep it completely different. Okay, so the next one is the molding machine. A choice of the molding machine is extremely critical. So for example, you can't make a very small part on a very big machine. You're never going to get that consistency. Okay, so that's the next one. And then the last one is the molding process. The last one is the molding process. I was, related to just like being a relay race, right? In a relay race, you can have, Usain Bolt, the fastest runner in the world out here, or you can have, if it's a swimming competition and you can race it, you can have Michael Phelps out here, and where does the pressure come on? The last guy, right? The processing guy, Usain Bolt or Michael Phelps. Man, if you had just run that 0.1 second faster, right, you would have won the race. But nobody talks to the guys behind them. Right? What about the part designer? What about the guy who selected the material? What about the guy who built the mold or designed the mold? Right? And the scheduler who scheduled the machine. Please don't get me wrong. If there's anybody in the audience who's a scheduler, I'm not picking on something that way. But typically, what do? You typically put the mold in a machine that's empty. Oh, that machine is empty. Let's put it in there. It doesn't work like that. Believe me. Okay, it just doesn't work like that. So all these things are extremely important and they carry weight. Okay, and I'll tell you the reason you have a process engineer, the reason I've been in business for the last 10 years is because all these people making mistakes. So in some way, thank you to you all. But I find these things, right? The process is actually relatively very simple out there. So the consistencies we talk about are cavity to cavity consistencies, the short to short consistencies, and then the run to run consistencies. Okay, all these things. I will, by the way, send me an email request. I'll send this to you as a PDF file. So don't worry, there are certain things I'm going to go really fast because that's not related to the design thing, but I'm just giving you some information here. And then a run to run consistency is the last one, right? So just if I've gone too fast, cavity to cavity consistency, short-to-short consistency, and then the run-to-run consistency are the three things, right? So the main reason why you don't get these consistency is the way the plastic shrinks. It's not easily predictable. It's not the same areas in all the areas of the mold. They have their own values, and the biggest thing is processing parameters can easily influence the shrinkage numbers, okay? And that's why we can come up with all these things. So what we do is that there are so many of these process settings on the molding machine: times, temperature, speeds, pressures, and positions, and all this stuff. They all have to be optimized to come up with a good, robust process. What's a robust process? It's like putting your car on cruise control and driving on the freeway. Then you don't have to basically worry about it. You don't have a cliff process. That means you're not driving on the cliff. They're constantly afraid that you're going to fall out and make bad parts, right? So we have all these things, and therefore what you have to do is that you have to optimize these things if you want to run your process in cruise control. And if it's not, then then you're going to get bad parts, right? So molders, what they do is they do scientific molding studies, okay, what I call a 6-step study, okay. Scientific molding is a term by Mr. John Bozelli and the people from RJG. They've come up with these things. I've added a couple things here and changed a few things. I've got my own ways of doing these things, and I call them the 6-step study, and then after that, also mainly what I do is design of experiments, right? So DOEs tells me that between these temperatures and these pressures, or whatever these things are, you can make parts within specifications, right? For me, the big step is this cosmetic process window, right? Which basically tells you between what temperatures and pressures or what parameters can you make acceptable parts cosmetically. Once I find out that limits, then I use those limits for DOEs, and then I will say, okay, between these limits, I can make parts that are now dimensionally acceptable. Okay, so by doing those DOEs, it tells me, if I go up and down, this means this is where I can change. These dimensions can go out of spec. This is a very stable dimension, or this, there's another dimension that I cannot make, so on and so forth, right? So DOE tells me how good my process is going to be. Okay, so I get an operating process window. That means if I've got injection speed, holding pressure, mold temperature, melt temperature, and cooling time, I have a process window. That means I can basically change the pressure, the speeds from here to here, or pressures from 800 to 1200, so on and so forth, if I want to be within specifications. So that becomes my operating process window. So I do this in 2 steps, right? The first one is mold qualification, then I go into selecting the actual process out there. And then I say, okay, this is the process where I can make parts within specifications, okay? Then what happens? Okay, so now let's get into the part design part of all this stuff. Okay, then what happens is that I've come up with this process which says the short size should be this, the cooling time should be this, the holding pressure should be this, pressure should be 975. Why should it be 975? It's only then can I make parts that are going to be within specifications. Okay, if I put my pressures to this value here, it's going to be out of spec. Okay, so I come up with these things and say, therefore, this is the most robust process. I can actually put a cruise control on this and then start running the press, right? But then what happens is that they say, man, you know what? These parts are breaking during injection. I can't make these parts because now when I mold it, when I was running this prototype mold, no problem. The customer accepted this and said I can use mold release. And because I can use mold release, I didn't care about it. It was ejecting fine. But now when I try to eject it out, the customer says I can't use mold release on this part, on this production mold, and now they're all breaking. So you can see here, right? This is actually, it's not very clear, but there's a ballpoint pen here and showing there's a break in this area. The sharp corners, it's breaking over here, right? So what does the molder do? It says, oh, let me go reduce the mold temperature, okay? And maybe that will help me out. So now it'll freeze off on the right side, wrong side, something like that. He goes and change it. One of the solutions that they do, okay? Or they're breaking during assembly. That means now what happens is that, see, that's the reason you have to also understand variation. Sometimes you're right at the edge. If the process is right at the edge, sometimes you're able to make good parts, sometimes you're able to, the parts, no matter what you do, the parts are bad. So let's say the parts are breaking during assembly. So what does the person think? Oh, you know what, I think it's basically going to, yeah, I'm packing it out quite a bit, so let me reduce the injection speeds, and because I reduce injection speeds, I don't have that much stress inside the part, and because of that, now I can make good parts, right? But as soon as it reduces the injection speed, what happens? It goes into this area. It basically goes out of spec, right? If I go back to this thing here, He goes out of spec. He goes in this area and says, man, now I can't make good parts. Or he changes the holding pressure, which is the worst thing to do, right? He changed the holding pressure because I'm packing it out so much, let me pack it less. See, holding pressure, by the way, is the biggest contributor to the dimensions of the part, okay? If you want good dimensions, consistent dimensions, you need to make sure that you pack out the part, adequately to the required amount, okay? Even your CPKs, your process capability, gets affected if you do not pack it out correctly. Because if you pack it out right, you keep on getting the same amount of molecules inside the cavity, and your process capability increases, consistency increases, right? So in this case too, let's say I'm stressing the part out. Let me reduce the holding pressure. So now he reduce the holding pressure. So now he goes out of spec, right? So then what happens is that basically by changing that, you go out of spec, and now you start going out of your window. Your molding window is supposed to be here. You end up going in this area or this area. Now you have parts that are barely going to be within specifications, and worse, they're never going to have that tolerances. So they're going to have a lot of variation, and so now you don't have the tolerance to go up and down that you can actually have good CPKs, right? So sharp corners is definitely a bad idea, right? On any molds. In fact, you look at any parts that are broken, 9 times out of 10, they're probably broken because of the sharp corner on it. That's the first thing. Multiple things. I mean, there's multiple things that I can actually go on. But second thing, let's say that I've seen is the rib thicknesses are more than 60 to 70% of the wall, right? So if you can look at this, there's a rib over here. There's some sort of a handle here. My friend Vikram Bhargava, that I'm going to talk about him a little later. He gave me this picture, and he showed me this, right? So if you look at this picture here, what do they have? They have a lot of sink in this area. Okay, why? Is because this is a very thick section. So this is considered the rib, and this at the back is basically that is the wall. And now if you look on the opposite side, you have rib thicknesses out here, right? And yes, does this matter to you? Sometimes it's a cosmetic area, right? So what do you tend to do? You tend to pack the part out quite a bit to get rid of the sink. Once you start packing this area out, you are definitely overpacking the rest of the parts, right? The rest of this rib starts getting overpacked, and then you develop a lot of stress in this area, and then it's too stressed, right? Even you say, no, I will just texture and take care of it. Yeah, you can put a texture, but you're just masking the problem. You still have stress built up in the part, and stress can really, cause havoc, during service. I'll try and show you a video at the end of it that again Vikram gave me. I'll show that to you what stress does to polycarbonate here. Okay, so rib thickness ratio, right? And that's another important thing that you need to look at, right? Therefore, you need to make sure that you don't have the rib thickness that's more than 60 to 70% of the nominal wall. Okay, plastic flow from thin to thick. Same thing happens. You go from thin to thick. The thin section that starts to flow, right? If it starts to flow from here, this thing freezes up faster. And now once this thing freezes up, there's no way you can get plastic in here, right? And now when you do that, what does the molder do? He increases the melt temperatures. He increases the mold temperatures, and he tries to inject it really fast in there, and he packs it out in there. As he packs it on there, all the rest of it gets packed out, and you might get rid of the sink finally, but I tell you, you'll never be able to get good parts consistently in that case, right? So that's not good. Okay, plastic flow from thin to thick. Okay, you can cause sink. Then sometimes when the surface finish is not acceptable, they increase injection speeds. And again, that's because of the way the plastic flows. In some cases, it does not flow. So same thing, right? This is related to this picture here I showed you is related to the surface finishes out here. You're not getting good surface finishes because it's not packed out well, right? And then that's what I was saying over here. Voids in the part, they increase the packing pressure. Stress in the part, it's huge. You can cause stress in the part by doing multiple things, okay? And that's one thing that must be also checked. Unfortunately, it's not a QC check, so really people cannot check it in the QC lab, but the designers need to understand that where the stress can be, can come into the part during the molding process. You have to understand that part of it. Uneven wall thickness. The biggest reason that you have warpage is uneven wall thickness. Okay, so if you don't have the right wall thickness, that means this is now less and this is now more. what happens is that this part, it freezes up very fast, and then this part, it keeps on shrinking because there's so much mass of plastic in here. And so if you've got uneven walls, because of the shrinkage that happens, you get a part that looks basically, will look like a U in this shape. This will be pretty much straight, but this part is basically rise up or rise down, go down, and you'll get this warpage in here. Okay, this is not the picture I'm going to show you here is not because of uneven wall thicknesses, but it's because of uneven cooling. Same thing happens if you have uneven cooling. You can think of this as this is uneven cooling here. So this thing is a very interesting picture. Okay, I think I should make this blow this up a little bit so you guys can see this. I should have done this right. So if you look at this thing here, what this is, this was a runner from a 3-plate mold that was coming out. Okay, and the operator was taking this and throwing it in a bin. When I looked in the bin, all the runners had curled up like this. And what's that for? Is because the inside out here, this area had less amount of water lines, and therefore this side was getting cooled less than compared to this side, right? And so what's happened, this side was hotter and kept on curling up, and basically it was getting a total warp part. Of course, they're not in the business of making runners, but now you can imagine what can happen if you've got uneven cooling inside the part, right? As soon as you have got uneven cooling inside the part, this is what tends to happen, right? So again, you need to make sure that you've got good cooling across the part, and again, you need to make sure that they are always therefore within that molding parameters. Okay, same thing is basically uneven wall thicknesses, right? One is thick, one is thin. You tend to have the same issues I just talked about this, right? You've got issues with warpage, or sorry, with the non-fill sections. I just decreased warpage, right? I discussed warpage. So this morning, by the way, I got an email from one of my clients, or one of the people who bought the software, and they said that, Suhas, how do I set tolerances so that my guys don't change it? Okay, so that basically goes tolerance in the molding machine so that my guys don't change it. They change the process, and he said the reason that happened is because one of the parts was warping really bad, so the technician decided to basically decrease the mold temperature, but only on one side of the mold, right? And that's exactly what happened here, right? If this is getting hotter and this is now very cold, so what do is that I change this temperature also to match this temperature. So now this temperature and this temperature are same. When this runner comes out, it's going to stay flat or flatter. Okay, but that's definitely not. He had an 80-degree difference between this side and this side. Okay, definitely not a good thing. Just to compensate for the bad mold design that they had in there, right? Definitely not a good thing. Actually, the mold will get damaged, not just the parts. Will have other issues with it, right? So he said that, this morning he said, how do I set those tolerances? So the answer to that, by the way, on my website there is a knowledge base that you guys can read through, and I've written a white papers or a paragraph how to set highs and lows or tolerances for molding process limits. So please read that when you have a chance. Non-fill section, right? So here's the thing, right? Huge problem with race tracking out here, okay, or hesitation flow. Plastic comes in from here, starts to fill here, it starts to go in here, but then hesitates to fill the rest of the part. So what happens? You get this this void on the inside. Okay. Are there ways to get away from it? Yeah, absolutely. When you're doing a part design, first thing is that don't make, see how thick you can make. If you can have even wall thicknesses, you can have flow leaders, you can have flow restrictors, and they'll be able to it, and you can basically, have the part flow evenly, and they can get rid of this, and then, that'll also help you, right? So again, what does the molder do with the part design that's like this? There is so many things that they do, right? They will increase injection speed, or sometimes they decrease injection speed, so it doesn't flow in here. They play with mold temperatures. If they've got different water lines somewhere, they'll increase them, center things. I mean, they do all this stuff. But see, all that stuff, it sends you to the cliff, and you get a cliff process, right? And that's not good, and that affects your process capability. Let's say this is a lens or whatever this is that has to actually fit into a frame. It becomes very difficult, to have a good capability in that case, right? Uneven draft angles. Okay, and this is another typical problem that you have, right? So you have to have good draft angles. Why do you have to have good draft angles, right? The reason is because, see, what happens is that you have got, let's say I'm making a cup. When the plastic shrinks onto the core, right? And as it shrinks onto the core, what happens is that when you try to now eject it out, you tend to create a lot of vacuum in this area, right? If you tend to create a lot of vacuum in this area, then basically what happens is that there's no way this thing comes out. So what they do is that you have to put a, of course you can put a vacuum and air pop it and get it out, but you don't have that luxury all the time. So therefore you have to have some amount of draft on the machines, on the parts, and that draft basically will help you eject the part out easier, right? By the way, Geometric has a software, the DFMPro shows all these problems on the on there. So it's a really neat software. I think using that will really tell you where the problems are. So if the parts do not eject, what does the molder do? The molder basically starts to decrease the cooling time. If when it decreases the cooling time, what happens is it basically will not hold on will not shrink as much, and if it does not shrink as much, now you can eject the part out faster. But see, by ejecting the part out faster than it needs to be, what happens is that you still have some heat built up in the part, right? So now you start getting a lot of post-mold shrinkage happening outside, right? So what should have shrunk inside the mold tends to shrink more on the outside of the mold, and that's uncontrolled. In this case, if the diameter is critical to you guys, then basically you can control that dimension inside the mold by letting it shrink to a certain point, and then ejecting the part out from there, right? So basically you have got, so like I said, the molder, what does he do? They will decrease the cooling time, okay? If they don't eject, they will increase the mold temperature. So now increase the mold temperature again doesn't decrease as much, right? Sorry, it doesn't shrink as much. And if it doesn't shrink as much, then again, you can eject it faster. But like I said, you're going outside your process control limits, your process limits, and once you start going out of there, then you start having issues with dimensions and therefore with capability. Okay, so that's not good, right? Tolerance specifications. Man, I can talk about this, quite a bit, but I'll keep it short. Is that basically tolerance? This is the other thing that I've seen, right? I think this is an area. I think this is worth discussion of its own, or rules, I would say, of its own. Okay, as an example, you've got a part that's 1 inch long, and typical tolerances are given as plus or minus 5 thousandths. But now if you go to a 5-inch part, right, you cannot give the same tolerance. You can't give plus or minus 5 thousandths. I've seen so many parts out there where the tolerances are given as plus or minus 5 thousandths. It's just generic, out there. It just says, if you look at the tolerance, the drawing, it says if it's 3 decimals, it's plus minus 10 thousandths. It's 2 decimals, it's plus minus so and so. It's 1 decimal, it's plus minus so and so, right? It doesn't make sense. How can you do that, right? So you have to. Why is that? Is because if you look at the data sheet, you always have the shrinkages are specified as inch per inch. So if you say that polyethylene is going to shrink 20 thousandths inch per inch, that means on a 1 inch part, you're going to get a total shrinkage from the mold, by the way, from the mold to the part. That means from the melt to the part, it's going to shrink 20 thousandths. Okay, and then there'll be variation. There'll be some variation in that. Now, but so therefore 20 thousandths for 1 inch, right? So now the part is 2 inches. If the part is 2 inches, then definitely it's going to now shrink 40 thousandths as an absolute value. If it's 10 inches, it's going to shrink 200 thousandths of an inch, right? So basically, what happens as the part length increases, the absolute amount of shrinkage keeps on changing. Okay, so therefore you cannot have tighter tolerances the same tolerances on a 1 inch part and the 5-inch part. As an example, I do not know, maybe some of you deal with micromolded parts or very small parts. You will never have dimensional issues as far as variation goes for a micromolded product. Okay, when I say micromolded part, I mean, don't think of a very small part. Even a part that is, say, 100 thousandths in diameter, or let's say 200 thousandths diameter, or a 1/4 inch in diameter, right? Well, 1/4 inch, you're pushing it, But let's say it's about 150,000 in diameter or one feature. Yeah, let's just take that. Just consider a feature on the part that you molded, right? Consider a feature that you're looking at, and that dimension, that height of a post or a hole diameter or whatever it is basically is about 100,000 or 150,000. Go measure 50 of them, or go measure 30 of them if you can, those posts or whatever it is, and see how much variation you get. You will not get that much variation. I bet you everything is within a thousands. Okay, everything is within a thousands. It's going to be very small. Whereas you look at the part, if it's a long part, then you see more variation there, right? So on that whole dimension, or the post dimension, which is say 150,000 long or 150,000 diameter, on that one you can actually specify a plus minus of even 1,000, and you'll be in spec. If you make it 1,500, you'll be very capable. Of course, now the CP and CPKs, when I say very capable, I mean very consistent. Your CP values will be very good. Your CPK values might be out, but whatever it is, look at the variation. Your variation is going to be within plus minus 1,000. I bet you on that stuff. Okay, so the smaller the dimension, the less tolerance you can have. The bigger the dimension, the more tolerances you need to give on there, right? Also, if you have a material that shrinks differently, right? That means if you're previously making this material out of, let's say, an ABS, 30% glass-filled ABS material, you're making out of it, and then your boss says, you know what, this is too expensive. We need to go to polyethylene or a polypropylene. And say, oh yeah, polypropylene, it works fine. It's got good properties. But now, whatever tolerances you have for ABS is not going to work for a polyethylene material, because polyethylene works. I mean, it shrinks differently. The shrinkage value is huge. On the other hand, if you go to a glass-filled LCP material, right? If you go to a glass-filled LCP material, you can have higher tolerances, even more than what you had in the ABS, because LCPs hardly shrink. The shrinkage values are very low compared to anything else, right? So tolerances, you need to make sure that you have the right tolerances for based on the part that you're looking at, right? So you have to give realistic tolerances based on the material that you're molding, based on the dimensions of the part that you're looking at. Okay, so give consideration in the material section, as I said. I'm going to end the webinar if somebody has questions here, but I have to acknowledge basically Vikram Bhargava for his tips, insights, and some pictures he has given me. I'm going to share a small video that he showed, which is very interesting. Here, I'm going to just bring that up. Oops, sorry. It's still in here. Right, it's a really neat video that shows you how, this is, if you can't see it, just let me know. I think you should be able to see this. So what this is simply is that this is a tensile bar of made out of polycarbonate, which you can keep on going, you can keep on flexing it forever, right? Nothing happens to it. You can keep on bending it forever, and nothing really happens to this polycarbonate part. But as soon as you add solvent, which is the next video here, as soon as you add solvent to this video, to this part, you can see that, just a little bit of solvent there, it's just totally snapped off, right? And that's basically stress, and that's what it does, right? So this is basically, Vikram gave me this this video. I think it's a really neat video, and he has got a wealth of information, I can tell you. So Vikram is the guy. He was with Motorola for several years. He retired as a director, and he's one guy who understands. I mean, I wish I met more people like him, because he really understood the design aspect of it when it came to processing. Okay, he was on the processor side most of the times. So I think everyone should go understand that, and I know most of you are designers in the audience today. But just please understand that it's a relay race. We will not be able to win the race unless you guys also help us out with these things and get us good quality products, right? Also want to thank Geometric for giving the opportunity to present. That's my contact information there. I'm based out of San Diego, California. Down here, I've got my own training location, training facility. Like I said, I do my own public seminars here. So if you guys need anything on that, those are two websites. I have software too, and lots of information on the website. So please feel free to contact me at any time. And that's my cell phone number. You can always contact me there. Yeah, good. So I think I'll end my stuff, and Rahul, I'll give it back to you. If anybody has any questions, I'll be more than happy to answer them.
Thank you, Suhas. Anyone from the audience having questions, please type them in the questions window, and we'll be happy to answer them for you.
Yeah, we have about, yeah, go ahead.
Yeah, we have a few questions coming in.
Okay.
So the first question is, which features typically contribute the most to molding issues?
Which features?
Yeah, the plastic part, which are the most commonly contributing features to typical molding issues?
So I think I'm not understanding the question very well. When they say features,
like ribs, bosses, undercuts.
Yeah. So basically, if you look at that, I think one of the main thing that you have issues with is what you just said, is when you try to take care of the sink on the parts, right? That is one big thing, right? Second thing is sharp corners. I think is the biggest thing that I always see that have issues as far as part designs, right? Then thin walls, right? I don't believe I brought thin walls in here. I should have also included thin walls, right? So thin walls is another huge thing, because when you have thin walls and you try to fill it out, at the end of fill, molders will try to basically pack that area out or increase the melt temperatures, and that causes us quite a bit of things, right? So mold design and part design are related. There's a huge relationship between that. So you can have a thin part, but then you need to have very good venting in the mold in that area also, okay? Or you can have on a thinner side, but you also need good venting, right? Any thin part has to have good venting, right? So I would say, by looking at these things, sharp corners, yeah, this is one of the major things that I see, especially if you can't take the parts out, including draft out here. Sink, yes, I see this quite a bit. Warpage, yeah, uneven wall thicknesses. I think these are the three main things that I think I always see that contribute to lots of issues that molders have in there, right? And then again, like I said, also I think part designers should also understand mold design, because putting where to put the gate locations, you might design a fantastic part, but if the guy puts the gate in the wrong location, then you'll never be able to mold it.
Okay, the next question is, why is it called a cosmetic process window? I think in your presentation you had one term.
Yeah. So I have a little bit of, I call it differently. I'll just bring up my software here actually. So okay, actually, even before that, let me see, how do I present this? So if you can't mold parts cosmetically, you can't mold parts dimensionally correct, right? I mean, basically, QC is not going to look at the parts if they've got flash on it or short shots on the parts, right? So I'm just looking at my, oh, sorry, wrong presentation. Yeah, it's right here. Right? It's like this. Unless you can make parts cosmetically, the QC guys are not going to look at it. So what I do is that I do what's called a cosmetic process window. That means between what processing parameters can I make parts that are cosmetically acceptable? So the two things that I always do, and that's why I said, right, my scientific molding concepts or studies a little different from other people, or those people have done it, right? So what I do is I will vary the melt temperature from the low to the high, and then find out at the low temperature between what pressures can I make parts cosmetically acceptable. right? It's like this, right? The way I teach in my seminar, right? And what you see here is my 4-day seminar, by the way. And in my seminar, I teach this thing, and when I talk about cosmetic process windows, you know, I always give an analogy of driving the car. You know, see, if I want to drive from, and that's a really nice slide, so I'll just let me tell you that. Okay, right. So you know what? If you want to drive, if I want to drive from San Diego to Chicago, and that's a distance of over 2,000 miles, right? If I say I want to go teach my seminar on Monday morning, I mean, I can't jump into the car on Saturday morning and say, let me drive there, right? First thing I need to make sure is what? I need to make sure my car is good enough of traveling 4,500 miles. That means that I need to go and come back, you know. So I need to make sure that that is good. Once my car is ready, and then I can say, okay, I'm going to put the punch in the address in GPS, and then I can comfortably start on, say, Thursday morning or whatever that is based on my analysis, and say I'm going to drive so many miles, stop, take a break, and then so on and so forth, right? And give myself some maintenance and things like that. So that is what is also with injection molding. You have to first make sure that the part is cosmetically, you can make the parts. And once you know that you can make the parts in a certain dimensions, in certain limits, then you can take those limits and apply to DOE. So if you're going back to the software now, I say that, you know, below 825 psi, my parts are basically, they have sink or they're shorts. Above 1275, the parts are basically, they've got flash, or they're stuck in the wrong sort of mode, some defect. That means what? Between these parts, these limits, I can make parts that are cosmetically acceptable. That means if dimensions are not important to my customer, I can sell it to my customer. Okay, I can sell those parts to the customer. Example, fork and spoons. Nobody picks up a fork and says, you know what, I think the distance between these two, the two tips here is 10,000 out, so I'm not going to eat from this. It never happens like that, right? So a cosmetic process window is that. And then what I do is I take this cosmetic process window, so I know these limits out here. I say, okay, then I say, okay, I'm going to go do a DOE on this. That means I do a designed experiment here. I say, okay, now at these settings, right? At these settings, where were my dimensions? I come up with this matrix here. I come up with the DOE. It's a very simple software. By the way, you use a drop-down menu. You select your molding, your factors that you want to see for DOEs. The next one, you put your highs and lows. So 1375, 925. See, below 925, the part has got shorts or sink. Above 1370, flashes, right? That's my cosmetic process window. Similarly, I've got these things here. And then what I do is I take these numbers. This is my nominals, highs and lows. I mean, my response name, what my nominal values are, and all this stuff. I click on worksheet. And then what the software does, it simply goes in and tells me, okay, you know what, go to the molding machine and basically run these 8 experiments that you see here coming up right now, right? Yeah, these 8 experiments that are coming up here. Once you run these 8 experiments, and again, this has been designed for injection molding. The user does not understand Taguchi methods. He doesn't have to understand any other statistics, nothing in there, right? You run these experiments, put in the information right here. Okay, they measure these things, and then I do analysis, right? Now see, this 8 experiments that you see, what is that? Those are the limits of my cosmetic windows. That means inside these things, I can make good parts. I can't go outside these parts anywhere, outside these limits, because I have non-acceptable parts. Then I simply, what I do is, I come in here, and of course it's a huge software. I come in here and say, the same thing I'm going to show you. And the same thing I'm going to show you, right? It tells me, see, now this is, if you look at this is my nominal value, 15.055. It tells me if I want to hit nominal, I click in here and say 82 degrees, mold temperature and 1035. I'm going to hit nominal, right on the nominal. Okay, it does this analysis for me, right? If I set my process here, 84 and 1276, upper spec limit. Out here, 98 and 947, lower spec limit, right? That means what? Now this window that I'm showing you becomes my dimensional process window. That means if I maintain my temperatures between 76 and 97 and pressures between 947 and 1204, I'll always make parts that are dimensionally acceptable. But this out here is my cosmetic window, which is my cosmetic process window. Okay, you can do multiple things. This is not a software presentation, so I won't go into details of this. I'll be more than happy. I do every week, I do a presentation of the software for people who want to see it and who purchase it. So I'll be more than happy. So please send me an email if anybody wants to see it. But it's very simple software that I have. Yeah. So anyway, yeah, we can go to the next question, guys.
The next question is, as far as wall thickness is concerned, where should the gate go?
The gate should always be in the thickest section of the part. Okay, so that you'll always fill from thick to thin. Okay, if you start from the thin area, then the thin area will freeze off faster. You'll never be able to pack out the thick section.
I think I'll take the next question, which is, does DFMPro address the design guidelines mentioned in this webinar? So yes, as Suhas mentioned during his presentation, DFMPro does address many of those guidelines which Suhas covered in the webinar, and not only for injection molding, but for other manufacturing processes as well, like milling, turning, drilling, sheet metal fabrication, casting, and it is integrated in the standard CAD system. So as a design engineer, you can use them for whatever parts you design and get the benefit of having the upstream manufacturing knowledge right at the design stage. The next question is, how do I know what's the right tolerance to add to my design features?
Well, first I think you have to look at your requirements, what your requirements are. You know, you might have to do, if it's an assembly thing, you have to do stack-up tolerancing, stack-up analysis and see what should it be to what you need to hold, right? And that's where I think as I said, you need to be realistic over there, right? Once you know that, I think then it basically goes into experience and some of the folks that are going to tell you I can or cannot hold this these tolerances, right? And also again, like I said, based on the molding process, right? So a molder, if he looks at it, he can say, you know what, I think I can hold this tolerance, I cannot hold this tolerance. You know, unfortunately, there are some rules, but unfortunately, there's still a lot of tribal knowledge out there for that purpose. But again, do a nice stack-up tolerancing analysis and see what it is, and then you can so you know what you should be.
I think we'll take the last question for now, as we are coming to the end. As a molder, I keep getting designs having such issues, and I do have to play around with the factors you have mentioned. But if I go back to the designers, the feedback is that it is a design requirement. So how do I handle such situations?
You guys are putting me on the spot out here. Well, this is always a battle, right? I mean, it's always a battle. So I don't have a good answer for that, to be very honest with you. You know, so the way I do this, and this is what I do, right? I will perform a DOE and say, look, these are the factors. These are my mold temperatures. I can't go above this for this reason. I can't go below this for this reason. Recommendations are so and so. Here's my DOE. Here are the 8 experiments, right? And this is the best I can do. Okay. There are 11 molding parameters, by the way, okay, on the molding machines, you know, and you guys should know. Again, you know, you should see that. So let me just say 4D somewhere here, right? There are 11 molding parameters on the molding machine that you can actually play with. When I say that, is basically what this is when you can play with. That is that directly influences your plastic. Okay, now of course there's mold open, close, ejection, all those things, right? But you're not looking at that. There's 11 molding parameters on the molding machine, that 11 plus 3 plus 2 actually, that you can play with, right? So what I suggest, and again, you know, is that you can basically say, look, I have done a DOE, right? And I'll tell you the 3 factors you need to do a DOE on. Number 1 is your melt or mold temperature. If it's a crystalline material, you do mold temperature. If it's amorphous material, you do melt temperature. You do second thing you do a DOE factor is going to be a holding pressure, and the third one is going to be a cooling time. Okay, for cosmetics reasons, you might require to play with injection speeds, right? You can do a viscosity curve, but I'll tell you the viscosity curve is the last thing that I typically do, or in my list. I do it first, of course, as per this thing, but as the one that I look last. Inject as fast as you need not what the viscosity curve tells you, or not what, as fast as you can. Because there's multiple things. Again, my website, I've written 11 reasons why not to do a viscosity curve, or not to use the data from a viscosity curve. So you might want to play with that, but that's it. Melt or mold, cooling time, holding pressure. You can go into pack and hold again. The difference again is written on my website. Please read that. And once you play with this stuff, give these samples to your molder. Don't spend too much time. Or they says, you know what, these are the highs and lows of all these things. This is the best we can do. And I'll tell you, that's the reason people have orphan tools in their shops, because some other molder is not able to run them, right? I'll tell you, as a consultant, when they call me and say, we need you to come and look at this process, I know when they call me, they have tried everything under the sun in the process, up and down, and they're still calling me. I know it's not a processing issue at that point. If it's a brand new mold, yes, I go do validations for them, I understand. But if they call me for a processing issue, I'll tell you it's not a processing issue, because I know before they spend the money to fly me there or to give me my consulting rate or whatever it is, it's always, they've tried everything under the sun, and it goes to being that. So my suggestion is, as a molder, make these parts and give it to them. Say, you know what, this is the best I can do. I don't think I can do better than this. I know they did not answer your question very clearly, but that's exactly what I do. I do not have a magic wand to solve all the problems. I tell them that.
Okay, so I think that's all we can cover for today's webinar. And thank you, Suhas. Thank you for your time.
Just one thing is that if there are more questions, what you can do is that email them to me. I know some of your questions has not been emailed, not been answered. You can basically email it to me directly, or to Rahul, or to the geometric guys, and I'll be more than happy to answer them at some point. So yeah, so thank you.
Yeah, thank you, Suhas. And thank you everyone for attending this session today. Please do attend our knowledge sharing session series, which will be held typically once a month or once every couple of months, and look forward to seeing you again. Thank you.